Reduction, preparation.
No, sir. We didn't do that.
So aldehyde and ketone are doubly bonded oxygen. Okay, you just have to put hydrogen. Okay, and if you put hydrogen, you will have singly bonded oxygen. That will give you alcohol. And addition of hydrogen is what? Addition of hydrogen is reduction. Okay, and how do you add hydrogen? You can tell me what you know. Yeah. Yeah, Nabil. You can try a bit. So you can use catalytic hydrogenation reaction. Okay. Catalytic hydrogenation reaction, you take some catalyst and H2 and you add HH. Okay, both HH will come and get added over doubly bonded oxygen and you will have CH2H. That is a primary alcohol. So aldehydes will give you primary alcohol. Okay, and this is catalytic hydrogenation, the most famous catalyst. Or your Ni is the most reactive. Okay, platinum, palladium. Okay, these are the other catalysts. And if you take ketone, so what you are going to get? If you take ketone, you are going to get a secondary alcohol because you have two alkyl groups. Is it clear, Nabil? And
Yes, sir.
tell me which alcohols cannot be prepared by catalytic hydrogenation.
Sir, tertiary.
Yeah, tertiary alcohol can't be prepared because in tertiary alcohols you don't have any hydrogen on the carbon, just have one OH. Okay, so tertiary alcohol cannot be prepared by this method. So you can have a look over here. NaBH4 is a mild reducing agent. Any idea what which type of substances get reduced by NaBH4? Which chemical compounds?
Sir, carbonyl compounds.
Yeah, which one? Which functional groups? Any
Aldehyde, ketone, and this NeBH4 only aldehyde and ketone.
pardon?
NeBH4 only aldehydes and ketones.
Aldehyde doesn't ketone. Yeah, and so, though this is not asked, but if someone asks you, they can reduce COCl also. Okay, aldehydes, but nobody talks about this. Okay, so but better you remember this one, aldehyde and ketones. Okay, and suppose if someone asks you RX also. Okay, if someone asks you this one and this one, but most commonly whatever you said is correct. Aldehyde and ketones are reduced by NaBH4, right? NO2 is not reduced. You can see over here. Okay, and you can take methanol as a solvent, alcohol, water. Okay, NaBH4 is a mild reducing agent. And what's the abbreviated name of NaBH4? Yeah, tell me.
Yes.
What's the abbreviated name for NaBH4?
Sodium borohydride.
Yeah, so SBH. Yeah. And which is the other reagent which is like NaBH4 but it is stronger?
The lithium aluminum hydride.
Yeah, LiAlH4, right? LiAlH4, and this is a better. Actually, these are hydride ions. Okay. So if you talk about the reduction, it is the addition of H minus. H minus is, it comes out and it attacks the partially positive carbon of C. That's how the reduction takes place. And then you take water. So this O minus which you get, that will be get converted to OH from the H plus given by the water. Clear? And being a stronger reducing agent, you LiLH4 can react with all the carboxylic acid and derivatives. Is it clear?
Yes, sir.
Aldehyde, ketones, carboxylic acid. carboxylic acid derivatives all. So if you want to do the selective reduction, go for NaBH4 ester, anhydride, amide. So let me tell you one very important thing. All of these will give you alcohols. Okay. This one will give amide. This is very, very important thing, which will be used in amine starter.
But sir, the CONH2 group is called amine.
Amide, carboxylic acid amide, or acid amide, and this is amine. But all of these will give you alcohols. They will give you only one alcohol, and these two will give you two alcohols, because this bond will get cleaved if you put H and H and H and H. So this will turn to alcohol. This will also turn to alcohol. Similarly, this will turn to alcohol. This will also turn to alcohol. So these will give two alcohols. Okay. Got it? Clear? But LiLH4 or NaBH4, they will not reduce carbon-carbon double bond. Why? Why they are not reduced?
Sir, because it is sp2 hybridized, more stable, and
But this is also double bond. What could be the reason?
it is non-polar.
Yeah, that is non-polar. Exactly. And that one C double bond was polar. And these are hydride donors, the H minus is coming out. So H minus, wherever it can easily attack wherever it finds a positive charge, but not on this. Same with the case with NaBH4 also. Okay. But you don't use directly on carboxylic acid, though they can reduce, because what happens, carboxylic acid have H plus, LH is having H minus, both will react and they will form hydrogen gas. So your LiLH4 will go waste. Initial LiLH4, you need to put more LiLH4, extra LiLH4 to reduce carboxylic acid. Okay. So what you do, you turn it into ester. Though you can, if the question come, you will do the reduction. Okay, reduction you will do. But if someone asks you, then you will say, you need to put extra LiLH4. Is it clear?
Yes, sir.
Okay. What about this one? Yeah.
Sir, two alcohols.
Yeah, LiLH4, yeah, two moles. Ester will get 2 moles of alcohol. Correct. Right. So just now I discussed for this portion.
Sir, can you just show the figure for the previous slide? Okay, sir.
Okay.
Yes, sir.
So LiLH4 is, yeah, it can hydrolyze esters, and you will ester and anhydride will give you 2 alcohols, right? They both can be same or different. That's a different matter, but two moles. Okay. NaBH4 will not reduce esters or anhydrides. Okay. So this one is clear.
Yes, sir.
Okay, good. So let's do this problem. So this is part of it is from alkyl halide chapter, right? Yeah.
Sir, methyl alcohol, ethyl alcohol.
Ethyl alcohol. So first of all, the CN is going to come in and it will displace the Br. This is CH3, C, and this you when you do it hydrolysis, when you do the complete hydrolysis, it breaks and it forms COOH. Okay, and when you have LiLH4, is it clear?
Yes, sir.
Ethyl alcohol is the right answer. Okay, yeah, let me write it over here. So what's the IUPAC name of P and Q?
Sir, the main reactant is what, sir? Is it benzoquinone?
And this is not a benzene, some cyclic molecule, which is there in front of you. Yeah, you need to think which are the what these functional groups are. Okay, and then accordingly with the reagent you need to take your decision. Got it?
Yes, sir. How will we name this structure, sir?
Actually, this you break with LiLH4. Is it clear?
Yes, sir.
So
Then
this
it
is going
will
to
form
change to OH.
state chain structure.
This is OH. Okay, and this is CH2 and this is also OH. Is it clear? So 1, 2, 3, 4, and 5. So pentane 1, 2, and 5 triol. Is it clear?
Yes, sir. Then NABH4 also will get same compound.
NABH4, what you will get? This is the structure of P. NABH4 is very selective, so this is ketone, and but that one is ester. Clear or not?
Yes, sir.
So the ketone will get reduced. This is lactone. Okay. So this one. you will get. This question is very important. You need to know the structures. That's very, very important. Clear?
Yes, sir.
Right? There is one mild reducing agent. Suppose if you want to take that as used for the preparation of aldehydes and ketones. If you take ester, okay, this is ester, and if you took NaBH4, it will not be reduced because ester, the resonance, it undergoes resonance, so it is less reactive, right? That's the problem with the ester. Yeah, Kulsum. Sorry, I've not seen. I hope you are. You can ask your doubts also. Okay. I thought that you are not there. So esters actually they don't react with NABH4. Okay. So also we were talking about the reductions, and NiLH4 is a strong reducing agent. So it is going to reduce this. Okay. And LAH, and it will break into two parts, RCH2OH and R-OH. Okay. They may be same or different. That depends. And there is one more reducing agent that is known as di-H. Yeah, what this stands for? This is abbreviated name.
Diisobutyl aluminum hydride.
Yeah, diisobutyl aluminum hydride. Yeah, correct. So this is isobutyl is this one. 1, 2, 3, and 4 carbon atom. And this is aluminum hydride. So this one. So actually it has only one H. LH was having 4 hydrogens, so it was actually it is a mild reducing agent, so it will also reduce ester, but it will give only one H. So what you are going to get? RCOH. Is it clear? Also, I hope you are getting it. Nabil,
Yes, sir.
clear?
Yes, sir.
Good. So let's move to, so this is the reduction method of preparation of alcohols. Okay, from aldehydes, ketones, carboxylic acids, and their derivatives. Okay, and similarly, you can prepare phenols also. So just this preparation of phenol we have seen in alkyl halide chapter also up to some extent. So if you have, so how can you prepare phenol? Just quickly tell me the methods which we discussed till now.
So from haloarenes, haloarenes, you can also
Yeah,
prepare it using by using from benzene sulfonic acid, from
yeah,
benzene diazonium salt, and from
yeah,
cumene.
yeah, exactly. Yeah. So you can prepare phenols from chlorination and doing the nucleophilic bimolecular nucleophilic substitution, that is Dawes process, by heating chlorobenzene at very high temperature and pressure. The OH minus is going to come and substitute this chlorine. It is going to form phenoxide ion because it is a basic medium, so you need to take some acid again to make it phenol. Yeah. The second method is, so this is the mechanism that what we discussed in alkyl lead chapter. If you have any doubt, you can ask me. Okay, this is the intermediate and electron withdrawing group make the attack of nucleophile very easy. Clear?
Yes, sir.
So now the next thing is, so you can see the more and more NO2 you have, the easily the reaction is going to happen. Next is sulfonation. You can do the sulfonation of the benzene by heating it with concentrated H2SO4 or SO3. You will have benzene sulfonic acid. The benzene sulfonic acid in the same way in which you displace the Cl by using NaOH, you can displace benzene sulfonic acid, the sulfonic acid, okay, by heating it with NaOH. Okay, and you will end up with a phenol. You need to take H plus to make it, because basic medium will convert it into O minus, and you need to take the H plus so that you can get the phenol. This is diazonium method. Diazonium salt to prepare from aniline. You heat it with the nitrous acid. Make aniline is heated with nitrous acid or NaN plus Cl. You end up with diazonium. You heat it with dilute H2O. Boil with dilute H2O. The N2 group break apart and the water molecules attacks in this forms. Okay, and this is which method?
You show the last slide for a second.
Yeah. Kulsum, is it clear? Any doubts? Let me know. You can stop me any number of times.
What is HONO, sir? Nitrous
What
acid.
is nitrous
HON.
acid? Yeah, HNO2, which is prepared during the reaction only by taking sodium nitrite and HCl. And also mention the temperature 0 to 5 degrees always. Actually, there was a question in NEET that there only was the temperature was different. And because of that, the reason association question that the option became incorrect. They have written everything correct. Everything was correct. But only what they have written is that the aromatic diazonium salt are formed by treating aniline with NaNO2 plus HCl at 300 Kelvin. They have written this. Just because of that only, just in NEET, okay, one month back, okay. And just because of this thing, the whole statement became wrong. Otherwise, everything was correct. So from this, we get two learnings. First of all, the diazonium, you need to be careful about the temperature. Okay, that is, while you are preparing diazonium salt, the temperature must be 0 to 5 degrees Celsius. Okay, the another learning is that you need to read each and every statement completely with full concentration. Okay, why I'm telling this? Because sometimes what happens, the initial part of the statement is correct and it appears that the whole statement is correct and we are familiar with it. It happens with many times. It happens with me also. Okay, so what is the solution? For example, in this, everything was correct except the last point, temperature, that was incorrect. So you, in order to avoid mistake, you need to check each and everything thoroughly. Okay, read each and everything thoroughly. Okay, I hope this is clear. Now we move on to the next method, cumene hydroperoxide method for the preparation of phenol. Okay, and what is cumene?
Sir, isopropyl benzene.
Yeah, isopropyl benzene. And how can you prepare it from benzene? You can prepare it by using Friedel-Crafts alkylation. The Cl minus will be extracted by AlCl3, which is a Lewis acid. You have a cation. It will go and attack on the benzene. H plus will be displaced by this isopropyl group. Okay, this
Yes,
is the
sir.
intermediate, right? This is the intermediate. You can have the same intermediate by other route. Also, is it clear? You can take propene also. Is it clear? So propene, you heat it with concentrated H3PO4 and
Sir, the
when,
second reaction is called what, sir? Second reaction.
pardon?
So first reaction is Friedel-Crafts alkylation, right, sir?
Yeah, this
What
is
is
also
second?
Friedel-Crafts. This is also Friedel-Crafts, but not the direct standard example of Friedel-Crafts in which you take alkyl halide and you take ALs also. You can take alkene also and the H plus catalyst also. That also comes under the Friedel-Crafts reaction. H plus will add in the Markovnikov fashion. Okay, concentrated H3PO4 you need to take. You have a cation, that cation is going to go and attack on the benzene ring, and the same thing you are going to. Or you can have alcohols also. The alcohol also you can have the same cation. Clear?
Yes, sir.
I hope this is clear. Also, right? Okay. So once you have this cumene, that can be obtained by different methods. So you need to be very careful about the methods which are given. Cumene may not be provided to you directly. This H is the most reactive H. Why?
It
Why it
is
is the
attached
yeah.
to, it is attached adjacent to carbon double bond.
Yeah, it is a carbon double bond, and this, because if it gets removed, the intermediate which you have in this place can undergo rearrangement. It can undergo resonance. It can be stabilized by resonance. You cannot rearrangement. Okay, is it clear? So
Yes,
that
sir.
will make it stable. So it can form very easily, right? And so when you heat it with oxygen in the presence of light or heat, this hydrogen is abstracted and the oxygen is inserted between the alkyl group and the cumene. Is it clear?
Yes, sir.
So what happens over here is, this is cumene hydroperoxide, and this is the compound which is responsible for the name of this reaction. Cumene, one side you have cumene, you have hydrogen, so it is cumene hydroperoxide, right?
Yes, sir.
Okay. And what happens is, these peroxides are very fragile. These peroxides are very fragile, so they break in the presence of acid. Okay, so remember one thing. Remember one thing. So this thing breaks as acetone, and this pH get migrated to this oxygen. Actually, a lot of steps are there. You have phenol and acetone. Acetone is a byproduct. Is it clear?
Yes, sir.
Right. So that's how we get this. So let's do this problem quickly.
Sir, C, sir.
Yeah, this is very simple. Cumene hydroperoxide. Yeah, correct. So this is asked many times in JEE. mains, advanced, everywhere. About this. Yeah, tell me.
Sir, is it D?
Which one?
B, B.
Second option.
Yes, sir.
Also, many idea. It is going to be. Actually, sorry, I have got some messages. So always remember in all the chapters, if you have a carbocation, always check whether it can undergo rearrangement or not. Clear?
Yes, sir.
Now tell me.
Sir, then D. Fourth option.
Which one? D. Yeah. Actually, the carbocation which was formed immediately after the extraction of Cl- was the primary. It has undergone rearrangement by shift of H. Okay, and you have a carbocation in the middle. Okay, and this carbocation actually will go and attack on the benzene ring. So this is again cumene, right? Always remember. Clear, everybody? So this is the main thing. Now you have the hydroperoxide and followed by hydrolysis, which will give you phenol and acetone, right? Now let's talk about, so this is the phenol, preparation of phenol. Now let's talk about the acidic strength. Alcohols are acidic. There are two types of reactions, okay? And if you are breaking H plus, the acidic strength is going to be more for primary, less for secondary, and least for tertiary. Why? Any idea? How will you explain me?
Sir, can you say again, sir?
Why this is the acidic order of the acidic strength, that the tertiary alcohol are least acidic?
Sir, because the alkyl groups are electron donating and they will increase the electron density on the carbon atom, on the oxygen atom.
Yeah, actually,
They
whenever you, any question, whenever you think about the acidic strength, what I do is I remove H plus, and whatever I get, that I call, that is known as conjugate base. You know, conjugate base of alcohol, that is alkoxide, and now I think whether it is going to be stable or not. If it is going to be stable, then the H plus will go away. It will never come back. Means the your alcohol is more acidic. But if this O minus becomes unstable, then it will bring in H plus back. Clear?
yes, sir.
So if you have more and more alkyl groups, the alkyl groups are not electronegative, they are electron donating. So they will make the O minus more rich because of their electron donating tendencies. And if your O minus become more rich, why it will let H plus go away? The minus, if it become more minus, it will attract H plus more strongly. So H plus will not go out. Okay, is it clear? So if this is a strong acid, what it means, the conjugate base should be weak. Strong acid will have weak conjugate base. Weak means stable. Stable means its electron density is less. It is dispersed. And but if you have a strong conjugate base, then your parent acid is a weak acid. It is not going to give H plus. That means. I hope that is clear,
Yes, sir.
right? So you can see many alcohols are there. Look, this is a tertiary alcohol. So acidic strength and pK, how they are related? Any idea? Acidic
Smaller
strength.
the pK value, greater is the acidic strength.
Yeah, acidic strength actually is measured by equilibrium, and with the measure of equilibrium is Ka, dissociation constant. So more an acid is going to dissociate, more is higher is acidic, the higher is going to be dissociation constant. So acidic strength and Ka are directly proportional. But pK is minus log of Ka. pK actually is minus log of Ka. So when you put minus, a larger number becomes smaller. Clear?
Yes, sir.
Right? So the order of pK is reverse the order of acidic strength. And you can see that the carboxylic acids are more acidic than alcohol, aliphatic alcohol, and then you have water, and then you have carboxylic acids, then you have actually phenol. Why phenol is more acidic than water?
Sir, because in resonance, the phenoxide ion formed is more stable.
Yeah.
Sir, one more thing I have thought, sir. Sir, in the phenoxide ion, they're saying that it is more stable because in phenol, although phenol and phenoxide ion both have charge distribution, charge delocalization. In the case
Yeah.
of phenol, there is a charge separation. Sir. What does that mean?
In case of phenol,
Yes, sir. You're saying phenol is having charge separation, whereas phenoxide is not having charge separation.
actually phenol is neutral. No? So when it do resonance, there will be a positive charge on oxygen and negative charge on the carbon. If a neutral molecule, the electron will go here and there. There is going to be positive and negative charge going to appear on various atoms. Clear?
Yes, sir.
It means there is a separation of charge. But in the case of phenoxide ion, it's just minus. So, and the fact is phenoxide ion is more electron rich than phenol because this is O minus. Clear?
Yes, sir. So hydrogen atom, during resonance, electrons will reach oxygen atom, will not gain positive charge.
Hydrogen atom.
So in phenoxide ion, during resonance, when electrons will go away from the oxygen, that time it will not get positive charge.
No, actually it is already minus. No, if it is already minus, if it gives its electron, it will become neutral. See over here. This is minus because H plus has gone. So this is minus. When these electrons come over here and form a double bond, these pi electron need to be shifted away in order to make the space for the incoming double bond. This is minus. So minus, it will remain minus, but this O will become neutral. Minus will come over here, it will come over here, it will come over here. So, but in phenol also this will happen. The minus will come over here, but actually the donor atom was initially neutral, but once it gives its electron, it will acquire positive charge. Clear? Right? Any doubts?
No, sir.
Okay. So why phenol is stronger acid than water? Bit stronger than water. What is the reason?
It gives proton more easily.
Yeah, actually the minus conjugate base has stabilized itself. Conjugate base, which is found after the removal of H plus, which was having negative charge, was able to successfully disperse its negative charge on ortho and para positions. Clear? And if it has successfully dispersed its positive charge or negative charge, is it going to come? Is it going to join? Will it have more tendency or less tendency to join back with H plus? Will the tendency increase or decrease?
Decrease.
If the minus charge is dispersed, will it want to join itself back to H plus, or will it, the tendency to join with H plus decrease? Will it be more or less?
Be less, right? Sir?
Yeah, it will be less because the negative charge is dispersed itself. And that is the reason why you have it. That is the reason why you have this. Okay. Phenol less, sorry, more acidic than water. Carboxylic acids are more acidic and sulfonic acids are further more acidic. What is the reason? Carboxylic acid also the minus will come after the removal of H plus, and this minus will undo resonance and it will get distributed on two negative charge, two oxygen atoms. And in this case, it will distribute itself on three oxygen atoms, which is in turn a good thing. Clear?
Yes, sir.
Right? So this is how the acidic strength works. So this is the resonance structure. You can have a look. And why cyclohexanol is less acidic? Yeah. Why cyclohexanol is less acidic than phenol? Suppose that someone asks you what you will answer.
Sir,
The
the
answer is there in
cyclohexanol
front
is,
of. Yeah, pardon?
sir, phenol is having double bonds because
Yeah,
the carbon atoms will be sp2 hybridized, so we pull
yeah,
the electrons more from the OH group.
yeah, yeah. And the negative charge which is formed after the departure of H plus will able to stabilize itself by distributing itself on the benzene. So now its tendency to combine back with the H plus will decrease. But in the case of cyclohexanol, there are no double bond. If the H plus is removed, O minus forms. If O minus forms, it is going to stay O minus. That's it. And if it remains O minus, it is going to become more unstable. And if it becomes more unstable, okay, it will not release its H plus. So cyclohexanol is actually less acidic. I hope it is clear.
Sir, but when we're drawing resonance structures, we show that oxygen is having 6 electrons. But in the above figure, Viper is not showing any electrons, sir.
Actually, the person who is asking the question will show you the lone pair whenever they are not required. They will deliberately show you, and wherever they are required, they will not show. Okay, it's our duty to know. Okay, that there are lone pairs. Is it fair?
Yes, sir. So
Especially
there are 6, there are 3 lone pairs.
there are actually on which one?
No
Ox-
oxygen,
yeah, oxide ion. Yeah,
copying oxide ion, sir.
yeah, exactly. As especially you need to be very careful in chemical bonding, because what happens is they will ask you beryllium fluoride and HCF2. Will they have same hybridization? You will say okay, yes, because both are F2. But when you look into the details, actually beryllium fluoride is like this and HCF2 is like this. Is it clear? The examiner may not necessarily or will not show you the lone pair. So make it a habit to check if there are lone pairs on the central atom, because that is going to affect many of your answers.
Yes, sir.
Okay. And now can you compare the acidic strength of nitrophenols? So what is the acidic strength of phenol, orthonitrophenol? I'm interested in this one mostly. Metanitrophenol. Paranit. Yeah. First of all, tell me whether the nitrophenols are going to be more acidic than the phenol or less acidic.
More acidic, sir. More acidic.
Yeah. So if you have electron withdrawing group, they are going to make the O minus more stable by pulling their electrons. Okay. So what happens here over is your, actually your H plus will come out very easily because the groups are pulling electrons, right?
Yes, sir.
So that is very important. Okay. And but it is also important to see where the nitro group is placed with respect to the OH. So which nitrophenol is more acidic? So first of all, tell me, will it be metanitrophenol or paranitrophenol? First, compare this one. Yeah.
Sir, it will be para.
Why para?
Sir, because the nitrogen atom is taking the electrons during resonance.
So,
But
but
in
one,
the,
yeah, correct. Your answer is correct. But one may argue that the para is far. How can the nitrogen take the electron?
sir, because due to resonance, it will come, the electron density will come on the ortho and para positions.
Yeah. If it is the nitro group, you can take the advantage of the nitro group by it will have. You can see over here. This is accepting the electrons. So more dispersal of negative charge means more stability. So that's very important. Okay, right. So para-nitrophenol is more acidic. So nitro group is going to withdraw the electron density from the OH if it is placed suitably at para position or ortho position, because ortho position also the negative charge is passing. Is it clear?
Yes, sir.
Now tell me.
Yes, sir. Then, which will be more acidic, sir? Ortho or para?
You tell me first. This is a very famous question asked many times in NEET, JEE mains, everywhere. So tell me. Yeah. Tell me.
Sir,
Yeah.
is it para?
Yeah. Why para? So para, then ortho, then meta, and then phenol. Why para? Hmm.
Sir, because in resonance, either the in resonance either the electrons can come from either of the ortho positions. So, but in the case of para, there's only one option,
Yeah.
like
No,
only one.
actually, yeah, someone may say that the nitro group is nearer. There is an inductive effect also which is operating, and this is more electron tendency, pulling tendency is more in nitro, ortho nitro than para. But then, in spite of that, should make ortho more acidic, but para is more acidic. Why? Actually, what happens here is in orthonitrophenol, the H, this is true, whatever I am saying is correct, but there is one more thing which you need to think. In orthonitrophenol, the H gets stuck inside by intramolecular hydrogen bond. Is it clear?
Yes, sir.
So this, because of this intramolecular hydrogen bonding, the H finds it bit difficult, not very, to come out. Okay,
Yes, sir.
so that is the reason. So para overtakes ortho. Is it clear?
Yes, sir.
Very important question asked at many places. Matlab, it is just like means it can be asked anywhere, right? Very important. Okay. So I hope this is clear. Okay, let me take you to the, and if you have more NO2 group, definitely that is going to be more acidic. If you have NO2 at all the three positions, ortho and para positions, so that will be picric acid, which is having three NO2 groups, and that is very acidic. Okay, the name itself has acid. Is it clear?
Yes, sir.
Okay. So chemical reactions of phenol. So one is nitration. So normally what is the nitrating agent? What you
We
use
use
for nitrates? What?
concentrated nitric acid and concentrated sulfuric acid.
Yeah, exactly. But here you have taken only dilute ethanol. Why?
It is more reactive.
Yeah, if one is more reactive, no need to take the concentrated HNO3. The phenol itself has high electron density. Okay,
Yes,
clear.
sir.
So you don't need uh, more nitronium ions. So you take dilute HNO3, that will work. But what will happen if you would have taken concentrated HNO3 and H2SO4 also?
So all 5 positions will have nitrogen NO2 groups.
Yeah, not all five, all three. Why all three?
Sir, but already with concentrated HNO3 itself, we'll get all 3, right, sir?
So when you do concentrated HNO3 and H2SO4, all three, because there you have minus charge. You have more accurate nitronium ions generated in the reaction, so more reaction at all the positions. Clear?
Yes, sir. Sir, but already with concentrated HNO3 itself, we won't be able to get trinitrophenol.
Pardon?
Just with concentrated HNO3, we can't get trinitrophenol.
Yeah, with trinitrophenol, and not only this one, there is a problem, very big problem, and this is a very electron-rich ring that just now we have seen that is in structure. And nitric acid actually is a oxidizing agent also, and the one who is electron-rich can lose its electron more easily. So there is a lot of black charry product which is formed by the oxidation. Okay,
Yes, sir.
of phenol. So the yield will not be proper. Clear? Right?
Yes, sir.
And that's the main problem. So now, so you need to take dilute HNO3, that will be sufficient. And now what? Halogenation, there again a problem persists. So now tell me how you are going to overcome this problem.
Sir, can you say it, sir?
Yeah, why you have one bromine attached, only one bromine attached when you have used bromine in carbon disulfide? But why you have three, all the orthopara positions getting substituted by bromine when you took bromine water in water? This is water. Bromine water, you will get tribromophenol, which is a white PPT. But in bromine in carbon disulfide, you will have only one bromine attached. Why?
Sir, because water is polar and CS2 will be non-polar.
Yeah, exactly. Water is polar, so what it will do?
It will polarize the bromine molecules, atoms.
Yeah. No, not only it will polarize, actually it will polarize the phenol to phenoxidine. The phenoxidine can dissociate easily, and phenoxidine is much more stronger than the phenol. This is non-polar. And non-polar, actually the phenol will not dissociate. Clear?
Sir.
This is also a test for the phenol. So test for the phenol actually. So you put bromine water and you end up with white PPT. Clear? So I hope everything is clear. But don't hesitate to stop me anytime if something you don't understand. You can ask me any number of times. Okay.
Yes, sir.
Okay. Good. So now there is another reaction, Riemann-Tiemann reaction. Very important reaction. So first you can tell me what you know about this reaction. Then I will tell you the details about it.
Sir, phosphated phenol with um, aqueous NaOH and with chloroform, and then we will get one intermediate substituted benzyl chloride. So when this is
Yeah.
hydrolyzed in an alkali, in the presence of an alkali, it will
Yeah.
give salicylaldehyde.
Yeah. Correct. So what is the intermediate which is formed for, in what phenol uh, in basic medium, what it forms, and the chloroform and base what they form?
Sir, the NaOH, it will form sodium phenoxide. The chloroform, it will form the phenol with CHCl2 attached.
No, that is later. I'm talking only about this one. That is later. This are you're talking about this one. I'm just talking about this one. You are correct, but I'm talking about the intermediate. Actually, chloroform HCl get removed and it forms because base removes HCl, and this is going to form what it is. What this intermediate is known as.
Carbon dichloride.
It's but it's not normal. It is carbene. Clear?
Yes, sir. Carbene.
It is known as carbene.
Carbamine. Carbene.
Carbene, yeah.
Carbene.
We have so it is neutral. It is having a lone pair and a vacant orbital. But neutral doesn't mean that it is going to be stable. It is highly unstable. Very unstable. Very unstable because it is electron deficient. Is it clear?
Yes, sir.
That's the main problem. So now it so phenoxide is having a negative charge on the ortho para position. So it will ortho positions are 2 and the para is 1. So this will get attached. So you will have a minus charge, right?
Yes, sir.
There was H plus which was not shown earlier. Now I am showing because I am going to use it. So this is the intermediate. And this actually want to regain its aromatic character. This want to turn back itself to benzene. So H plus actually will be removed and this you will have this. Now this will get hydrolyzed. You will have 2OH on carbon and that will change to double bond O. And that's how you get salicyl aldehyde.
So which one will react first, sir? NaOH or CHCl? CHCl3?
Pardon?
Sir, which one will react with the phenol first, sir? The chloroform or the NaOH?
This dichlorocarbene is going to react with the phenoxide. Is it clear?
Yes, sir. So first, so which step in the will the NaOH attack, sir, on the phenoxide ion?
Which, pardon?
Sir, when will the NEOH attack on phenoxide?
NaOH attacks on phenoxide, it is abstract the H plus. Okay, you have this phenoxide ion form, and phenoxide ion is a nucleophile and this is an electrophile. They combine together. Is it
Yes,
clear?
sir.
So now the H plus
Yes, sir.
is removed by the C. This becomes C minus. It abstract H plus, and phenoxide ion again have its basic benzene character, right?
Yes, sir.
Clear?
Yes, sir.
That's how you need to understand it. So now these two Cl are hydrolyzed by OH. You have two OH and that will change to C double bond. And finally, upon acidification, you will have this. Clear or not?
Yes, sir.
So this is the mechanism. Now let's do some question.
Sir, could you just show the slide one more time? Okay, sir.
What's going to be the answer to this?
Sir, is
Yes,
it A?
it is going to be no. Just now I told you the
Sir, D.
which one?
D.
D, dichlorocarbon. Right. Okay.
Sir, but uh, what will happen to the chlorine and hydrogen, sir? It will come out as HCl on dissolution.
Yeah. Actually, first of all, the H, because this is a basic medium and base removes HCl, so H plus and Cl minus are removed. Clear?
Yes, sir.
Right?
Yes, sir.
There are two more reactions which are studied along with the Riemann reaction, but they are not Riemann. But there is a similarity, little bit. They appear to be same, but not same. So phenol, if you treat it with NaOH and carbon dioxide, what you get? That is pole-based Schmidt reaction.
Sir, we would get salicylic acid.
Pardon?
Salicylic acid, right, sir?
Yeah,
Yeah.
salicylic acid. Yeah, so this is quite simple. You have negative charge over here, and CO2 is an electrophile. It is having a polar bond, partial positive charge, partial negative, partial positive, partial negative. Oxygen is more electronegative. This negative charge is going to come and join in on the carbon. there is a pi bond which gets shifted on O minus, and that's how you have.
How is CO2 polar, sir? It is having.
CO2 is non-polar. Its bond are polar. Overall, the molecule is non-polar.
Okay, sir.
Okay? But it has polar bonds, individual bonds. The net dipole moment is 0. So it is susceptible to be attacked by the carbon is having partial positive charge, so it can be attacked by C minus. So here also the same thing happens, and you have this COH, right?
Yes, sir.
And what about this one? What about another method which is used to prepare the salicylic acid? Yeah.
Can you repeat, sir?
What is the other method, other set of reagents?
Sir, we can first convert it into salicylaldehyde by using rivarotin, and then by using lithium aluminum hydride.
No, no,
We,
directly, not indirect, direct.
yes, sir.
Directly, you can use one more reagent, NaOH, and CCl, carbon tetrachloride. Okay.
Sir.
So actually, what happens here is here the reaction looks very similar, the reagent actually, but you need to look into detail. This is CCl4 that was. So now what happens is this minus here, the carbene is not formed. This minus goes and attack on the Cl. One Cl comes out. And you have CCl4. H plus is removed by the base, not by the CCl3 because it doesn't have minus. It again forms the phenoxide ion. It again forms its aromatic character. The OH will be, and the OH will go and attack on the Cl. 3 Cl will get removed, and finally you will have three OH. What just think in this way, and you will have water removed, and you will have COH. Clear? Is it clear?
Yes, yes, sir.
Right? And so that is also similar, but not similar because the product are different, the reagents are also different. But in first sight, they may look similar. Is it clear?
Yes, sir.
And that's a very important thing. Now the reduction and oxidation, zinc you can take, and zinc will remove oxygen. This is a reduction method, and you will get back your benzene. Till now, we have seen so many methods to get phenol from benzene. This is the only method to get your benzene back. And if you try to oxidize phenol, it can get oxidized very easily, as I told you, because it is very much electron rich, and you will have this as one of the product, benzophenol. Not very common reactions, but yeah, but very important also. Like basic reaction, just one line, you need to remember that, right?
Yes, sir.
Now to this question.
Sir, is it benzaldehyde?
It is going to be benzoic acid. So phenol upon treatment with zinc dust will
Sir,
change
it
to
will form toluene.
pardon?
Toluene at the end. Oh, it
Yeah,
will form toluene again.
yeah, toluene. And you should know that listen very carefully. All the alkyl side chain containing at least one hydrogen, benzylic hydrogen, at least one. Listen to me very carefully. All the side chain which contain at least one benzylic hydrogen, carbon side chains, alkyl side chains containing at least one benzylic hydrogen get oxidized completely to COH irrespective of the number of carbon atoms. Got understood?
Can you repeat again, sir?
All the alkyl side chain of the benzene ring containing at least one hydrogen, a benzylic hydrogen, will get oxidized completely to COH group.
Yes, sir.
That will get oxidized completely to COH, irrespective of the number of carbon atoms. So if you have methyl, ethyl, propyl, butyl, whatever you have, okay, they will get oxidized to COH. Clear?
Yes, sir.
Right? So that's a very important thing. And yeah. So this one now, let's go to another reaction. That is acetylation reaction. So what do you mean by acetylation? First of all, tell me.
Sir, addition of the acetic group on
Yes,
the
acetyl group.
yes, sir. On the alcohol or phenol.
Yeah, correct. So OH get acetylated. And what are the acetylating agents?
Sir, acetic anhydride in case of phenol, and
Hmm.
for alcohols, we will use carboxylic acid, carboxylic acid, acid chloride, and acid anhydride.
Yeah, correct. Right. So acetic anhydride. So either you can heat your alcohol directly with carboxylic acid. The water is going to get removed. And you will have water removed, and you will have ester. How will you know that the ester has formed? How will you know?
Sir, color.
Mm, but no, not color. That is a very important characteristic of esters. You must have studied it in your junior classes also. Actually, this characteristic help us to test alcohols or carboxylic acid by this method. And this is esters have fruity smell, right?
So what's it?
Fruity smell, fruit, sweet, fruit-like smell. The smell of the fruit is also because of the esters, right?
Yes, sir.
That is the very important thing. Okay, esters have fruity smell, and it is can be used to distinguish alcohols or carboxylic acid. If you have alcohol given, okay, you can put some acids and heat it with concentrated esters, right? And that will give you ester. You that will have fruity smell, right?
Yes, sir.
Okay, that is very important. But if you have, you can also use RCOCl like COH if you have. This is acetyl chloride. HCl gets removed. You take pyridine also. Pyridine actually is a base. It absorbs HCl, right?
Yes, sir.
So that will actually let you do the acetylation of alcohol. This is acetyl chloride. Or you can use acetic anhydride also. Clear?
Yes, sir.
This is the main thing. Okay. Now reaction with metals that we did already, but where it is used, reaction with metals. Actually, this is related to acidic hydrogen. Okay, and acidic hydrogen, if it is there, if you take electropositive metals like sodium, potassium, okay, they're going to displace the hydrogen. Okay, and this can, up to a certain extent, it can be used to detect alcohol, but not the type of alcohol. But you can detect whether you have an alcohol or an ether. Suppose if the formula given is this one, right?
Yes, sir.
And if they ask you, uh, is it an alcohol or an ether? How you will tell? Just quickly. They're not asking you the detailed thing. Not asking you whether it is primary alcohol, secondary alcohol, tertiary alcohol. They're just asking you the basic thing.
So we will make it react with the metal
Yeah,
based on the compound.
yeah. Very, very simple. You will put some pieces of sodium, and if it is an alcohol, okay, your alcohol will react with the acidic hydrogen, and what you will get?
Sodium alkoxide.
Yeah, sodium, and you will have liberation of hydrogen. Sorry. But if you have ether, you will not observe this liberation of hydrogen. Is it clear?
Yes, sir.
Okay. So that's the very basic thing. ethers. But the drawback is it is not going to tell you whether it is primary, secondary, and tertiary. So which test you are going to use?
Sir, Lucas test.
Pardon?
Lucas test.
Yeah, Lucas test. That is going to tell you whether it is primary, secondary, or tertiary. Now let's move on to your dehydration of alcohols. What do you mean by dehydration?
Removal of water molecule.
Yeah, and what you get as the product of dehydration of alcohols?
Alkenes.
Alkenes.
Alkene.
Yeah, and you just heat it with concentrated acid. Okay. And you heat it with concentrated acid and you have water removed, and that's how you get your alkene. Okay. But different alcohol undergo dehydration at different rate. Let me tell you that this dehydration actually is removal of, not the breaking of O and H bond. This is carbon oxygen bond. And if you have carbon oxygen bond being broken, the rate is going to be tertiary, secondary, primary, right?
Yes, sir.
Clear? So rate of dehydration. Why? Because
Sir,
yeah, the mechanism will let you know why. So
yes,
you can see, and the tertiary alcohol are going to get dehydrated most easily. You can see by the noting the temperature. Clear?
yes, sir.
Right? And why? So what do you feel? What's the reason behind it? Tell me. What's
So
the
the
reason that? Yeah.
ability of tertiary carbocation.
Yeah, actually the OH get protonated from the H2SO4. It comes out as water and the carbocation. This is the rate determining step. This is the main step, which is the most difficult one. And how can you make it easy? If you can make it easy, you can increase the rate of the dehydration. You can make the cation more stable. And how can you make the cation? Actually, we can make actually the nature of the alkyl group itself is going to make. And if it is tertiary, cation will be more and more stable, more branch cation. Now what happens, HSO4 minus, or you need to do is heat, you need to heat it. Actually, it is acid catalyzed. So acid initially helped by giving its H plus, borrowing its H plus to, giving its H plus to OH, that will make it a good living group. And finally this H plus will be taken back by the H2SO4 and HSO4 minus, or the water by heating the electron will get back to the carbon-carbon bond, and that's why you will have a double. So this is the mechanism. Rate is directly proportional to the stability of carbocation. Ethanol, for actually you don't have to remember for all the alcohol. A different alcohol will undergo get dehydrated at different temperature. This you need to know the temperature for ethanol because this is asked at many places. Is it clear? So what this temperature is?
213 Kelvin, sir. For forming to E. ether and 443 Kelvin for forming into the ethene.
Yeah, yeah, correct. If you have 170 degrees Celsius, it is ethene. You need more temperature for elimination. And this is not elimination, this is substitution. How it may have formed? Suppose this cation is attacked by another alcohol group. But this is not elimination, this is substitution. Substitution occurs at lower temperature, right?
Yes, sir.
And if you have further lower temperature, then also substitution will happen. That will actually give you this hydrogen sulfate. For ethanol, you need to know the temperature. For other, because it is asked directly. So you need to remember the temperatures. Okay. For other
Yes,
alcohol,
sir.
you can just compare. Let's. So what is going to be the? I think. Let me unshare the screen just a second. The very basic question. This can be wrong. Don't rely on this. Okay. You can tell me your answer. Yeah. So what's going to be the answer to this one? And okay, I think the time is already up. I forgot. Just we can do this question. Just quickly we can finish off this question. Yeah, so 3T dimethyl
Sir,
between yeah.
D, sir. D.
D. 3T dimethyl butadiene. Is this the answer? Is I told you one thing very important in that cumene chapter, the cumene reaction. The question came. Always don't forget to check for the possibilities of rearrangement of carbocation. Right? Now tell me. A carbocation can stabilize itself by moving on to adjacent position, right?
Sir, but how will the methyl group move, sir?
Yeah, actually it is a methyl shift. Actually, it forms a bond with both of them at a moment, and it breaks its bond. It pulls electrons from this point and get connected to the other point permanently. Now you have to make the most branch alkene. The two things you need to keep in mind. This is not going to be the answer. The answer is going to be this one. You need to make or check the possibilities of the rearrangement. That is the first thing. Once you have the most stable carbocation, then you need to make the most branch alkene, which is the most stable one, right?
Yes, sir.
That's how we are going to do.
Sir, but why is it named butene, sir? There are 5 carbons in the longest chain, right?
No, 4 carbon. 2,3 dimethyl butene. Clear?
Yes, sir. Sir, sir, what is the other group, sir? 2,3-dimethyl butene means is.
The
Okay, sir.
other possibility
Sir,
could
it
have